And now I'd like to introduce our speaker for tonight. His name is Norman Graf, and he's a physicist here at SLAC National Accelerator Laboratory. And as you'll see, he's eminently qualified to talk about angels and demons and tell us the truth about antimatter. Now actually, Norman began his scientific career by graduating summa cum laude from the University of New Mexico in mechanistic organic chemistry. But in 1983, when he was an exchange student in Europe, he traveled to CERN. CERN's an international laboratory on the Swiss-French border, which you're going to hear a lot more about tonight. And while he was visiting CERN, they discovered a very key particle called the W boson. And moreover, this exciting discovery was made possible by colliding antimatter with matter at very high energies. And so Norman was hooked by observing all the excitement here, and he underwent a conversion, as we call it, from chemist to particle physicist. He then did his PhD at UC Irvine, studying antimatter annihilation at very low energies. And then he went back to very high energies at another of our sister labs, Fermilab, and was part of one of the collaborations that discovered the yet heavier particle, the heaviest particle ever discovered, the top quark. In 2000, we were very fortunate to have Norman come to SLAC. He now splits his time two ways. One is back at CERN on an experiment called ATLAS, and secondly is to do research and development for sort of the next big thing, a linear electron-positron collider. But tonight, his job is to tell us all about angels and demons, the science behind the scenes.
Thank you, Lance, for that introduction and the safety here. So I think everybody now knows what you do in an earthquake, right? All right, obligatory joke out of the way. So let's go on. Welcome to SLAC National Accelerator Lab, part of the public lecture series that we've had here at SLAC. It's always well attended, but this evening seems to be an overflow audience here. Talk, as Lance said, is motivated by the imminent release of the movie Angels and Demons, a Sony production. It's directed by Ron Howard, stars Tom Hanks, and is based on the novel Angels and Demons by Dan Brown. So this evening's lecture is not only a part of the SLAC public lecture series, but it's part of an outreach program that was instigated by the release of this movie. And, as scientists, we also occasionally love to read some good fiction. And we're very appreciative that in this particular novel, science plays a role, which we will investigate for the rest of for this evening's talk. There are some websites, of course. There's always a website, and we'll get into that in just a bit. And there are over 50 different institutions scattered across the country, across the continent, and even across the world. So many so that I got tired of adding in little red dots where the talks were going to happen. But they're happening here in Palo Alto, they're happening in Pittsburgh, they're happening in Paris. They're happening in Vancouver, British Columbia, they're happening in San Juan, Puerto Rico. And they're even happening in the hinterlands of Spearfish, South Dakota, all the way to New York City. So we have full coverage this evening of the happenings, the imminent release of this movie. So how many of you have read the book? That's pretty good. How was it? How many of you seen the movie? Okay, since most of you have read the book, and since most of you who have not read the book will at least want to know what's going on, let me just give a brief overview of the plot without hopefully giving away too much to ruin the suspense of the movie. Professor Langdon, he's a professor of symbology at Harvard University. He gets a call in the middle, very early in the morning, and he's asked to help solve a mystery that his talents can be used to solve. He's flown to this place called CERN, four-letter acronyms beginning with C. You always have to be careful of those. So the question is, does CERN exist? In a hypersonic plane, even, that is sent by the DirectorGeneral of this mysterious lab. He descends into something called the LHC, tunnels deep beneath the Earth, and where he discovers containers full of antimatter. But even more important is what he discovers is missing. One of the containers is actually missing, and that is the crux of the plot of the novel. After doing this, he then leaves to the Vatican to solve the mystery of the missing antimatter, and since the doors are closed now, I can tell you this, that we are actually going to stay here and solve some of the mysteries of the universe. So here we go. It starts out early in the morning, 5:18 with a phone call. I must see you immediately. A German accented voice wakes him from his reverie. So of course, who is this? And it's Maximilian Kohler. I am a discrete particle physicist. I get this a lot. A what? Well, that's what we do here. We do it here at SLAC National Accelerator Laboratory. We do it at other national laboratories across the United States. We do it at national and international laboratories across the world, and of course, at universities all over the world. And most of what I'm discussing this evening addresses exactly what it is that we do. So he sends a plane, the Director General of this mysterious institution called CERN. It looked as airworthy as a Buick, has no windows, has barely even wings, it has dorsal guiders, just hull. It's a prototype of something called a SCRAMJET, and it goes Mach 15. And those of you into aeronautics recognize Mach as the speed of sound, 15 times the speed of sound. Pretty cool. Turns out, if you Google SCRAMJET, NASA has built one of these. And sure enough, it does look like a Buick, right? I mean, it's got these tail fins, and in this version, they're even chromed. This is a top view, a side view, and a front view, no windows, gold-plated, probably, which explains why it's so expensive. And this is actually a prototype, the X. It's not the X33, the X43, but X for experimental. And it turns out that this was actually successfully flown a number of years ago. NASA owns a Stratofortress. They strap this puppy onto the wing. They fly up to 40,000 feet. They have a booster rocket which takes it above 90,000 feet. And they then light the burner, and it goes to Mach 10. So we're not Mach 15, but they successfully tested the technology to use scramjets to go to very high speeds, so Mach 10. So the only thing that keeps this thing from being a commercial airliner, other than its looks, is a lot of engineering. Clearly there has to be a lot of engineering going on. But more importantly, perhaps, is a business model that returns on the investment of the people owning the companies. So scramjets exist in prototype form, but no, CERN does not have one of these at the discretion of the Director General. So he's flown to Geneva, and he's told that the flight takes an hour, and he's in Boston. And he's thinking, upstate New York, that should be pretty good. He hadn't reckoned in with the Mach 15. And so the pilot tells him upon landing, no, it's Geneva, Switzerland, not Geneva, North America. So what I want you to do now is to hold on to your seats. Everybody strapped in? All right. He just crossed 6 time zones getting to Geneva. Now, I just recently came back from a conference in Japan, and I got on the plane at 6 p.m. on a Tuesday afternoon. And when I landed, it was 11 a.m. the same day here at SFO. And believe me, it sounds a lot cooler than it really is. So, all right, you all strapped in? Let's go. Let's take off. We'll leave SLAC, leaving the Panofsky Auditorium, up and over the continental United States, across the North Atlantic, and descending into Geneva, Switzerland. There is Lake Geneva. There is Cointrin. All right. So he arrives. He's picked up. He's driven to CERN, and on the way, his driver tells him all sorts of exotic things. He tells him about quarks and mesons. He talks about no border patrol. You saw there we were on the border of Switzerland and France. He's zipped right through there at the Director General's behest. No checks of passports. Now, of course, that tells you when that was written. Today, you can also get across the border without a passport, but at the time, it was rather interesting. Mach 15 jets. Who are these guys, right? So we're talking about CERN. So how many of you have heard of CERN? Wow, that's pretty good. Was that because of the black holes which were going to swallow up the Earth last year? Yeah, I can understand. You guys are asking yourselves the same thing. First, it's black holes devouring the Earth. Now it's antimatter destroying parts of Rome. Exactly. Who are these guys? Well, it turns out that here's what the acronym originally stood for. It's changed in the meantime. But you look at this and you see European and you see maybe research and you hear nuclear and you go, criminies, what's going on here? And you might share Professor Langdon's ignorance about CERN, although since all of you have heard about it, you're one up on Professor Langdon. So anyway, welcome to CERN. What is CERN? CERN is an international lab. It's a regional European lab, but it is international from its very beginnings. It arose out of the ashes of the Second World War. Many of the lead scientists in Europe, as well as political leaders and intelligentsia, left Europe or were forced to leave Europe. And after the war, there was an attempt to reestablish some semblance of scientific research on the continent. And so CERN is actually one of the very first pan-European institutions that was set up. It was established in 1954. You already know that it's somewhere close to Geneva. It actually straddles the Franco-Swiss border. And the way I heard the story, it was located there because Vicky Weisskopf, one of the first director generals, really liked to ski, and the Alps are really close. There are currently 20 member countries from Europe. There are also another 15 or so institutions or countries which have visitor status, and the United States is one of those visitor status countries. Over 9,000 scientists are in some way associated with the activities going on at CERN. Not all there all at the same time, although sometimes when you're standing in line at the cafeteria, it seems like that. And there's about over 1,000 from the United States who are involved in the studies going on there. And this doesn't even come close to counting the number of technicians and engineers and support staff that go on there. So it's a very large international lab. And some of you have heard of CERN because that is where the World Wide Web was actually invented. It's mentioned in the book. How many of you knew that? Good fraction. Well, we do have a very technically and technologically literate citizenship here in the Bay Area, but Professor Langdon did not know that, and it actually turns out that Tim Berners-Lee in 1989, in the early 90s, did invent the World Wide Web to sit on top of the internet, which I understand Al Gore had something to do with, and came up with the World Wide Web. And a small connection here to SLAC is that SLAC was actually the very first website here in the United States. So that is some connection to that. So we come back to the Director General. This is the one who called up Langston at that ungodly hour of the morning. He's described as the Director General of CERN. He was known as König, or King Kohler. And they say it was a title more of fear than reverence. Now, this may have been true of previous Director Generals of CERN, but as of January this year, there's a new Director General, Rolf Hoyer, and I've worked with him quite closely for the past 10 years or so. And I understand from my colleague Eduardo that probably the worst thing you can say about Rolf here is that he's a bad goalie. So as he's being given a tour of the CERN laboratory, he's told that they possess the largest machine on Earth. And of course, the usual response is, you're kidding me, right? Are you telling me they dug out millions of tons of Earth just to smash tiny particles? And the answer is, indeed, they did. And this is how you start. First, you dig a very deep hole straight down. And just to set the scale here, these are people standing here. This is a concrete mixer in the background, so that sets the scale. So once you've gone down far enough, you start digging sideways. And this sets the scale of the tunnels here. So this is, very large machinery that you usually see rumbling down the streets, causing traffic jams. They actually lowered these a football field down into the earth, so 100 meters or so, over 300 feet, and then began tunneling sideways. And this is not just raw tunneling through the earth. This is glacial fill. It's not rock, and it turns out there are lots of underwater rivers and stuff. So this is a fully lined, fully reinforced tunnel that goes under the foothills of the Jura Mountains. And once you're done, you have a very large, almost straight-looking tunnel, but it turns out there's actually curvature to this tunnel. It's just so big around that you don't notice it at first guess. And then, of course, once you have this humongous tunnel in the ground, then you have to start building caverns, because the reason to do this is not just to build tunnels, is to do experiments. And these are extremely large experiments, and you need very large experimental caverns in which to put your detector. And again, here you see the scale. These are very large trucks and cranes and stuff. This is about a football field in length. It's about 80 meters in length. And the diameter, or the diameter of this is about 25 or 30 meters. So enormous vaulted spaces under the earth that are excavated. Here you see some more tracked vehicles even. And in the end, once you've puttied it up and put concrete around it, this is what one of the experimental halls looks like. And here's the access shaft. So 100 meters up is the surface. And for scale, once again, we have people standing in the viewing gallery here. And then you start instrumenting it. Why? Well, particle accelerator, they tell him, is going to be put into this tunnel here. And he's vaguely familiar with the term. And it brings back to him the memory of the superconducting supercollider. So it's quiz time again. How many of you have heard of the SSC, that big machine that was dug or started to dig in the plains of Texas? Yeah. They grow mushrooms there, yes. It was going to be the world's most powerful particle accelerator, and it was going to be one of the most important scientific prospects of the century projects. Unfortunately, it was canceled due to budget considerations in 1993. And here, just to set the scale, so this is even more enormous. Here is the megalopolis of Dallas. And here, surrounding the unfortunate town of Waxahachie, is a 54-mile-long footprint. And this was going to be the tunnel which would house the accelerator for the superconducting supercollider. It was 54 miles in circumference. And here are the access shafts and experimental caverns, which dwarf even those which I just discussed are at CERN now. And the energy was going to be 40 trillion electron volts. And an electron volt is what you get if you take an electron across a battery. So you go from the positive to the negative. So if you have a D-cell battery, that's 1.5 volts. And then you just string trillions of these together and you launch an electron. By the time it gets here, it will have this particular energy. Now, that's not how you would do it, or at least not how I would do it. But that gives you a scale for what's going on here. So just to give you a scale, what does that mean, 40 trillion? Is that a lot? Is that a little? Are we already doing that? Well, the world's champion currently for high-energy physics collisions is the Tevatron. And you got to love these names, right? Tevatron. At Fermilab, which is a national lab. It's one of the DOE Office of Science national labs. It's located about 40 miles west of Chicago. And to set the scale here, this is a 15-story high-rise. And on a clear day, you can see the skyline of Chicago 40 miles distant. And so here, currently, we have a 4-mile ring, and protons and antiprotons are accelerated and brought to collision at 2 interaction regions. This is the experiment that I worked at, and these are the other guys. And the energy at which they run is 2 trillion electron volts. So that sets the scale. This other project would have been 20 times more powerful. But that's old history. We need to move on. What can we do about that now? So CERN has a particle accelerator. It's a circular tube for smashing particles. We said that, but Langdon is a little slow, so you have to iterate these things over and over again. And sure enough, here it is. It turns out that when the SSC was canceled, CERN already had a rather large accelerator tunnel and detector cavern complex. It was called the Large Electron Positron Collider. It collided electrons and their antimatter partners, the positrons, in a circular accelerator, and it had 4 interaction regions with massive detectors. Here at SLAC, we also had an electron-positron collider, the SLC. How many of you have taken a tour here of SLAC? Cool, yeah. So that's 2 miles long. Up until recently, it was the world's longest building, but they built a terminal at Beijing International Airport, which is a little longer. So I don't know if that's a good thing or a bad thing. 2 miles, that's a long ways. But anyway, they had this tunnel. They had the detectors in there. They were almost done with it. When the SSC was canceled, they thought, what can we do with this tunnel? Well, they can rip out the guts. They can put in better electronics, better magnets, and use this then to do some of the physics that was envisioned for this failed superconducting super collider here in the United States. And they even envisioned the 2 large caverns that I just showed you for these 2 different experiments. So here it is. This is the footprint. When we landed, we were going Mach 15, so we didn't see too much of the scenery. Now we go back and take a little bit, again, a view of the Swiss-French landscape here. This is Cornevin, the airport. Here is CERN Headquarters. In the dotted line is the border between Switzerland over here and France over here. These are the Jura Mountains. And here is the footprint of the erstwhile LEP tunnel and now the LHC tunnel. And there are a number of other tunnels along the way. Looking the other way, this is my favorite view because here you get a view of the Swiss Alps, the French Alps. There's Mont Blanc. There's Lake Geneva. Unfortunately, when you're at CERN and you're sitting at the cafeteria looking out, if you can see Mont Blanc, you know it's going to rain. And if you can't see Mont Blanc, it is raining. But once, I spent a number of years there, trust me, it's a true aphorism. So once again, here's the airport, here is the headquarters of CERN, and here are the 1, 2, 3, 4, 5, 6 interaction regions, 4 from the previous experiment and the 2 brand new ones that were excavated for this new project. So here's the LHC complex. As I said before, it's about a football field under the ground, so you go down in these shafts. This is not to scale relatively, but that's why the labels are on here. So you go down 300 feet, and then we saw earlier you tunnel and tunnel and tunnel and tunnel and tunnel, and it actually, they met up within centimeters of one another. So an enormous amount of civil engineering in addition to high energy physics that went along here. And it's almost 27 kilometers in diameter, so that's roughly 16 miles around. So compare that to the Tevatron, paltry 4 miles, compare it to the SSC at 50 miles, it's better than what we had. And so for those of you who think I'm not being a good citizen and using acronyms that I have not yet fully explained, well, Dr. Langdon felt the same way. He's asking the LHC, what's that stand for? Trying not to sound nervous. And the answer that Kohler gave him was, it's the Large Hadron Collider. It's a particle accelerator. So previously it had been a lepton collider. That's one type of matter. Hadron are another type of particles. Briefly, and very, very high level, leptons are like electrons, hadrons are like protons. So in the atom, you have your nucleus and your electrons. Hadrons are the nuclear, and the leptons are the electrons. And so he's asking, this particle accelerator, I suppose it's down this tunnel someplace. And yes, indeed. So here is now the tunnel. This is the LHC tunnel now, the Large Hadron Collider tunnel. These are the hundreds of magnets which are used to steer the beam. These are superconducting, so just a smidge over absolute zero. They're filled with liquid helium, and they have superconducting cables, which are necessary to have the very high fields, the very high currents. And it turns out that the superconducting technology that was used, that was needed to develop the Tevatron at Fermilab and now the LHC at CERN, is the same technology that goes into the magnets that people use in MRIs. And so that the basic R&D that went into doing esoteric R&D for a physics collider has a spin-off in making MRIs, medically useful diagnostic tool, affordable. So here we are. It's a huge tunnel. You have to ride around on a little cart. It's 16 miles. You really don't want to be doing this on foot. And actually, you'll notice this little white line. There's a little photosensor. This thing drives itself just in case you fall off out of boredom or fall asleep. So there are fail-safe mechanisms all over the place in this tunnel. Here we have shot of a man in a wheelchair down in the LHC tunnel, and this is not Director General Kohler. This actually is, does anybody know? Yes, indeed, Stephen Hawking. The LHC was supposed to have turned on last fall. You probably all heard about it. So prior to that, it attracted an enormous amount of interest. We had members of royalty. We had heads of state. We had famous physicists such as Stephen Hawking here. We even had rock stars such as Black Eyed Peas come and visit. So to those of you for whom that means something, you can Google Will I Am and LHC, and you'll actually see a small little video, most likely on YouTube. So it's attracted an enormous amount of interest across the spectrum, from politics to science to entertainment. So what do we do there? So I've told you about this accelerator. I've told you a little bit about detectors. He gets a pretty good introduction in the book. You take these two very thin particle beams in opposite directions, and you then collide them head-on, one into the other. They drive into each other. They compress all their energy into a single pinpoint, and then they annihilate. And then we build these massive detectors to see what happens when they annihilate, right? Annihilate can mean lots and lots of things, and I'll go into a little bit more detail. So here is now one of the two major experiments at the Large Hadron Collider. It's the ATLAS experiment. And here is the experimental cavern, and here this tunnel, this is where one of the beams will come in, and the other one will come in from over here. And they will meet in the middle here, and they will compress into a pinpoint, and they will annihilate, and they will create all sorts of destruction. But you have to build a detector. And so here again, you see these large cranes, you see people standing down here starting to build this detector. And again, you start filling it in with all sorts of support material, readout electronics, large magnets. Here again is a person just for scale. And you cram electronics in there, you cram readout. Every square centimeter is precious in this environment, because you want to make the most out of the physics that happens when particles interact right there, smack dab in the middle. And here is an artist's representation of what might happen when these two particles come together and annihilate. You create a number of other particles. You take the very high energy and you combine them to create new matter and new particles. And just for those of you who are safety conscious, this person will not be standing there when the collision is happening. Or at least not very long. So we don't want any particles coming out and escaping and illuminating the audience here. So what we do is we put a plug in the end. So we seal this thing up. It's as hermetic as possible. Every little crack is filled with something, so we can see every little bit of what happens when these particles are brought into collision. So ATLAS is the experiment I work on, so it comes first, but it also comes first alphabetically. There's also another experiment called the compact muon spectrometer. And again, compact is sort of in the eye of the beholder, right? It's compact compared to ATLAS, which when it is finished, and it is finished now, is the largest by far detector or machine of its type in the world. So they took a different tack. ATLAS took this sort of ship in a bottle approach. So you drop everything down the access shaft and you build it, and you saw it being constructed in the cavern itself. What CMS did was they built it up on the surface, and then they lowered it. These are hundreds and hundreds of tons lowered by these very thin but very strong cables down the 100 meters down into the pit, and then they put it together there. It worked, it's together, and they're awaiting beam, so nothing fell. At least not that we can talk about. Once again, here for scale is a person, and he did get out of the way before this was mated with that and brought together. So once again, every single square centimeter is instrumented to find out where these particles go. So what happens when we annihilate these particles? Recreating the Big Bang. That is the way it was described in the book, and that's the way you've probably heard it in the press or on the web. So just to remind you, the Big Bang is the current reigning theory for how the universe was created, something like 14 billion years ago. The supposition is that equal amounts of matter and antimatter were created. And so the question is, what happened? Because obviously, when you go into a bar and the bartender says, "Hey, buddy, what's the matter?" you can say, of course, well, everything, right? Because we don't have antimatter that we know of in our local environment. We have matter. We have bits and pieces of rock and wood and concrete. So what happened if there were equal amounts of matter and antimatter created? At least two. There's always at least two answers, right? Slight differences in matter and antimatter caused the imbalance. So maybe it wasn't equal amounts that were created. Or they decayed differently. They were created, but they weren't created equal. And so in the intervening 14 billion years, something happened to the antimatter and left over the matter. Or just early on, they separated, like the two kids on the back seat of the car. You separate them, and then they don't interact. So maybe that's just what happened. We don't yet know. So Mr. Langdon, he's confronted with this when he's told about the missing antimatter. I sense you've heard of antimatter. And, the usual sort of response is, yeah, well, sort of, yes. How many of you have heard of antimatter? Jeez, you're such an easy audience. Okay, well, we'll describe what's going on here. The history of antimatter actually goes back to a famous theorist, Paul Dirac, Swiss theorist, back in the 20s, who combined relativity, remember our favorite equation E equals mc squared, which Einstein had derived in 1905, and quantum mechanics, which was the theory for how matter interacts with matter and electric fields and magnetic fields and stuff. And so this was developed in the early 20s, and in 1928, Paul Dirac was able, through a very incredible feat of intellectual calculation, came up with the combination of relativity and quantum mechanics. And it's now called the Dirac equation. And surprisingly, this doesn't always happen, but surprisingly, he not only came up with the equation, he also came up with solutions to the equation. And it turns out that he had solutions that had both positive and negative energy solutions. Now, it's hard for us to think of negative energy. It's not like a balance sheet where you have, positive and huge, gigantic negative budget deficits. But it's hard to think of what negative energy means. And it took a while for them to understand that this actually predicted a mirror universe. There should be as much antimatter as there is matter. And so, as I said, it was an intellectual tour de force for him to come up with this, come up with a solution, and then come up with an interpretation of that predicted a doubling of everything that we know to be true about nature. So you create the matter and the antimatter, as they discuss in the novel, Angels and Demons. How do you separate the particles? Well, it turns out, and I've already alluded to it, sorry, there has to be some forward referencing, otherwise I'd never get started. It turns out if you have charged particles moving with some velocity and you have a magnetic field, the charged particles will bend. One will go right, one will go left. And that's what they tell them. Matter arc to the right and antimatter arc to the left. And that's how you can then separate the particles from the antiparticles when you've created them. And lo and behold, 1933, just a few years later, Carl Anderson down at Caltech had a particle detector called a cloud chamber. And the cloud chamber, I have one set up over here, and maybe after the lecture we can turn it on and see if it's working. It's a very humid environment, and as charged particles go through this humid environment, they cause raindrops to form along its trajectory because they're charged and they ionize the gas. And so you have small little raindrops fall where the particle went. And so Carl Anderson had one of these in his lab, and he just happened to have a strong magnetic field lying about, and he had a thin sheet of lead, and he just took pictures of these traces of particles coming from the cosmos called cosmic rays, and we might be fortunate enough to see some later. And here we go. This is the discovery of antimatter. You have a particle coming in from the top. It's arcing to the left, so it's antimatter. It goes through the material here, and you can see that this curvature is slightly less than this, and it turns out that the energy that it lost tells you that it actually came from the top, right? Otherwise, you wouldn't know whether it came from the top or the bottom. So in 1933, Carl Anderson discovered antimatter, and rather coincidentally, Paul Dirac shared the Nobel Prize for his theory of relativistic quantum mechanics. So then we moved on. Experimentalists now had twice as many particles to look forward to. That's always a great thing. But you can't rely on little droplets of rain in a gaseous chamber, so you have to make more complicated detectors. The next big thing that came along, and literally big thing, these are people once again, is called a bubble chamber. So now instead of having a vapor that you condense to make rain, you have a liquid which is almost boiling. And when a particle goes through here, you start to boil the liquid. And so you get bubbles again forming, but it's the formation of those that tells you exactly where the particle went. And they would take millions and millions and millions of pictures, and they would have hundreds and hundreds and hundreds of people looking at these pictures, just looking one after the other until they found something interesting. And this is what, oh, sorry, getting ahead of myself here. So particle of matter and a particle of antimatter, when they combine, they release two new particles, because the matter and the antimatter annihilate, turns into energy, and then you get two new particles coming out. And here's a bubble chamber picture. This is familiar to a good fraction of you, I'm assuming, right? You've seen these in arts, in websites, et cetera. And this is a photograph. A beam of particles came through here, interacted with the material in the liquid, and these are the bubbles where the liquid started to boil, where the particle actually went. And you can see that there's a strong magnetic field, and so they're actually curving left and right. And here, actually, you have a particle which didn't leave a track. All of a sudden, you have matter, and you have antimatter being created. And this just became routine. You would have millions of pictures like this to pour through to look for the discovery of new material. And there is just a schematic, so people would go and calculate exactly what was going on there. So we've discovered the anti-electron. As most of you know from high school, atoms are made of protons and electrons, so if there's a proton, is there an antiproton? Well, that took almost 20 more years to discover, and it was discovered right across the bay up here on the hill at the Tevatron. And again, you gotta love these names. The old days, they had names like Tevatron, Cosmotron, Tevatron. Nowadays, we have LHC, PEP2, KEKB. We've lost some of that spirit of interesting names. But anyway, what they did was they had a beam of antiprotons, which they then captured, and this is a picture of the actual antiproton coming in to rest and then annihilating into oodles and oodles of particles. Now, those of you who are paying attention recall that I said when a matter meets antimatter, they give two new particles, and how come there's 9 here? Well, it turns out that protons, again, remember your high school physics, are not basic particles. They're made of quarks. And so it's the quarks inside the protons which are annihilating, and that's why you get lots and lots of particles coming out. The next day, New York Times, in its usual style, new atom particle found, termed a negative proton. So this was the discovery of the antiproton. The Berkeley Gazette had a slightly different headline. Seems somewhat appropriate for Berkeley, right? It's a grim new find at UC. Now, why did they say this? Well, it turns out that one of the scientists who was being interviewed let it slip that if matter meets antimatter, then they annihilate. And, of course, that's pretty grim, right? So in the book, I said we went down into the basement, and they had containers of antimatter. So what's up with that? If matter and antimatter meet, how can you have containers of it? Well, you can't store antimatter inside a normal jar. You got to do something a little more intricate than that. You got to have something, antimatter traps, obvious, right? These exist. And they're called penning traps, not because you're penning antiprotons, because it was Dr. Penning that actually came up with it. And here's the schematic. And what you do is basically you have very high vacuum, so there's no material for the antimatter to interact with. And you have magnetic and electric fields. Magnetic fields, remember, steer matter. So if you can steer it to go in a little loop, it never gets out of the vacuum, so you can actually keep this and have a bottle of antimatter lying around. And if you're really careful, you can actually move it around on a cart, like I said, very carefully. So I was at CERN in 1986 when the first experiment to capture antiprotons in one of these penning traps occurred. And they very successfully decelerated these protons. You know, normally we accelerate them to high energies, smack them into each other. But they wanted to see, what is this antimatter? Is it really, you know, the opposite of matter? So you got to trap a couple of them and actually look at them. So they managed to store a couple, and they kept them in this bottle for quite some time. Almost the very next day, the headlines in La Suisse. Now, if you're like me, I didn't read French at the time either, even though I lived there. But you can sort of figure out here, right? Antimatter, something, something, boom. Right? So this article, that was the headline. That was the headline. So here's the accelerator. This is LEAR. That's where I did my thesis, the low-energy antiproton ring. It's a small machine that nobody ever talks about, and it allows blah, 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 blah. But this last little thing here, it attracts the attention of American and Soviet scientists. And these Americans, some were from American universities, such as I was, but there were also scientists from Los Alamos. So, what the heck were they doing there? Well, you turn the page, bingo. There's a schematic of an antimatter bomb published in 1986, days after CERN successfully stored antimatter in a pending trap. So I'm not saying that the plot comes from reality, but it is true that people were worried about antimatter bombs as soon as they were discovered back in 1955 at Berkeley, and then at CERN when they were bottled and available for transport. So, antimatter bombs. What's the deal here? Why are they even of interest? Well, the attraction here is because, as I said before, you have matter and you have antimatter, and when they come into contact, they annihilate into a mass of particles. And so what, right? We have TNT, we have nitroglycerin, we have all sorts of explosives. Well, chemical reactions of that type, so chemical bombs, release about 1/billionth of their weight in energy. About 1/billionth or so. If you're talking about nuclear reactions, fission or fusion, you get about 1,000th. So if you have 1,000 grams of something and you explode it, 1 gram of that goes into energy and into destructive power. Antimatter, it's 1-to-1. You don't get any more bang for the buck than antimatter if you want to build a bomb out of it. So, how big a specimen did they have? And it turns out this was the biggest bottle. Of the hundreds of bottles that they had down there, it was the biggest one that went missing. And it turns out it was a full 1/4 of a gram. And if you express that into kilotons, that's almost 5 kilotons. And that's about 1/3 of the yield of the bomb which destroyed Hiroshima, and the bomb which destroyed Nagasaki was 20 kilotons, so a factor of 4. So, 1/4 of a gram of antimatter is a heck of a bang. Which, of course, leads you to all the rest of the book, which I'm not going to talk to you about, but should make an interesting movie. So the question is the threat real? Should we worry about antimatter bombs? Should we call up the Department of Homeland Security and say, geez, I just saw a diagram for an antimatter bomb, you got to do something about this? Well, the answer is no. We make very, very little antimatter. We make it particle at a time, and usually we use it to annihilate exactly at the same time because we're interested in using it as a tool to understand the mysteries of nature. Fermilab, which I told you before, is the world's champion creator of antimatter, creates 2/billionths of a gram of antiprotons per year. And I see some of you already doing the calculation in your head. Anywhere close? 109 million years to make a 1/4 gram. So better get started now. And it turns out that the Large Hadron Collider doesn't even collide protons and antiprotons. They gave up on that. They just could not afford to make enough antiprotons to do the science that we want to do at this collider. So we actually collide protons on protons because you just can't make them. Speaking of which, how do we make antiprotons? Well, once again, E equals mc squared. This is one of the few if you're going to memorize an equation, this is a good one to have on your top 10 list. You take energy and you turn it into mass. So what we have is we have a beam of particles, we accelerate it to very, very high energies, and then we smack it into something heavy. Usually it's a uranium target or a heavy metal target, and all of that energy that's in this one particle goes into a spray of other particles of different masses, different energies, different angles, etc. And how many of you were counting the number of red tracks in those productions? There weren't very many, right? Those were the antiprotons. So you produce all the scads of other particles that you don't really care about, and you only produce an antiproton every once in a while. And then sometimes it's pointing off in the wrong direction. So the efficiency for generating antiprotons is extremely small. Only a high-energy physicist would ever be interested in actually doing that. So the question is, can we use it as an energy source? Well, not really. I just told you it takes all this energy to make it. You're not going to get anything near that amount of energy back. But, you know, people are interested. So Tom Hanks, when he visited the Atlas experiment in preparations for the movie, he asked, you know, he was sitting there with a cup of coffee, it was early in the morning, could he keep his cup of coffee warm with antimatter? And the answer is, well, sort of. Obviously, if you have enough antimatter, you can make 5-kiloton bomb. But if you took all of the antimatter that is going to be produced for the Atlas experiment, and you sort of, you know, stuck your coffee cup into the middle of this detector, careful not to spill it because you're going to ruin some electronics, it would raise the temperature about 1 degree per hour. That's it. All of the collisions at the Large Hadron Collider, this ginormous 16-mile accelerator with these hundreds of or thousands of ton detectors, and you know, you can't even keep your cup of coffee warm because it would cool in that time, right, by about 10 degrees. So, you know, you're still losing. So it's not a very good energy source. And then the next question is, it's antimatter, right? Antimatter, does that fly up? So here's the question. You have an apple, it falls to the earth. You have an anti-apple, what does it do to the anti-earth? It's a good question. We're scientists, we ask these questions all the time. And as near as we can tell, we have absolutely no reason to believe that they don't fall exactly the same. There's a theorem, CPT theorem, that you can Google if you want, that ensures us that everything that we know to be true about nature tells us that an anti-apple falls to an anti-earth exactly the same as an apple falls to the earth. But that's not what we're asking, right? We're creating antimatter here in the lab, so we have an anti-apple and we have a real earth. What's it going to do? Fall up? Fall down? Don't know. But rest assured, we have, you know, experts on the task of finding out what's going on here. So there are experiments. As I said, they started back in 1986, and they're ongoing. It's incredibly difficult to you know, put one of these single antimatter particles on a scale because it annihilates right away. So you have to come up with some pretty good things to do. But anyway, they're working on it. A number of experiments are asking this question here. And then, of course, once you know the answer to that, the next question is, does a anti-helium balloon fall down? So next question, an anti-world. This is discussed in the book here, that you could actually play creationist and build an anti-Earth and anti-universe. And again, human beings are very inquisitive, and physicists are sort of the inquisitivist of all the humans. And so we do things like we make antihydrogen. So we created positrons, which are the antielectrons, right? And we've created antiprotons. And, you know, some very smart people have figured out how to bring the two together to make antihydrogen and actually study it. So this has been created and it's been studied not that long ago, but it's been studied. And then you get into esoteric things, because the next one up would be helium, which has 2 protons and 2 neutrons, but here you'd have to have 2 antiprotons. And then these antineutrons are really tough because they're hard to corral. But what we've done is we've taken helium and we've replaced one of the electrons with an antiproton. And remember, the antiproton has a negative charge. So it's sort of lopsided. You know, it's got this cam action that goes around because this is 2,000 times more heavy than that. But you can actually make an atom and study what's going on. And then even weirder is this thing called positronium. And you can tell this was postulated a long time ago when they still had cool ideas for names of things. It's an electron and a positron. And you're going, wait a second. Didn't you just tell me that electrons and positrons annihilate when they come in contact? Well, that's true. But if you think of ice skating, think of the annihilation as hockey. You know, these two players, they really want to run into each other. And when they do, things come off, like helmets and sticks and sometimes teeth, right? So it's a real hard collision, interaction, things go on. So if the electron actually hits the positron, they annihilate. But using the ice skating analogy, in ice dancing, you have the pairs, they come to each other, and they don't hit. They have some distance between them, and they conserve angular momentum, so they start spinning one around the other. Now, my wife always tells me that I'm always conserving more momentum than she is, but we don't annihilate. We don't run into each other. And that's exactly what happens with positronium. You can study this stable state for a very short period of time before they annihilate. So I was a chemist. So most of you recognize this from your chemistry days in high school. There we are. We've made antihydrogen. We have a long, long, long way to go. And just for the benefit of the rest of you chemists out there who are saying, hey, where are the actinides and where are the lanthanides? This is your lucky night. There they are down there. So we have even more. And then once we've made all the elements, then we have to start making molecules, and then we have to start building bigger things, and then pretty soon we're making rocks and boulders and bigger and bigger. So don't hold your breath. It's not going to happen anytime soon. So another thing that's touched on in the book. What? Oh, how many of you saw the movie? Cool. I haven't had a chance. I was busy writing this talk all weekend. Was it any good? It occurs to me that we could have had a really, really cool talk on the science of Star Trek. Who would come for that? All right. Okay, I'll talk to the organizing committee. Maybe we can get somebody to do this. The USS Enterprise. Matter and antimatter. Why aren't we using that for rocket propulsion? Well, as hard as it is to make antimatter, it's even harder to make dilithium crystals. So that's the limiting factor. It really is. But, people look into this all the time. RAND, which most of you recognize as a think tank, has commissioned studies on this, and they asked the question, could we use antimatter for deep space drive? And it turns out there are a number of ways you can do that. You can simply use matter to annihilate with antimatter, and then use the heat released to boil off a liquid, just like you do in a nuclear reactor where you boil steam to turn a turbine, except here you just take the high temperature exhaust and use that to drive the rocket. And then you can use also antimatter to initiate fusion reactions. Remember the headlines in La Suisse where they had a fusion reaction. You used antimatter instead of a nuclear or atomic bomb to start a fusion reaction. Now this, you really, really, really need some good shocks on your rocket. What else can we use antimatter for? Well, it turns out that here at SLAC, we have been very busy looking into astrophysical evidence for antimatter. We're looking at evidence for the Big Bang. We're looking at what goes on in the cosmos. Remember I told you there should be lots of antimatter out there. Why isn't it there? And we're trying to understand exactly what goes on. And it turns out, once again, we can convert photons, these particles of light that come in from the cosmos. If we could convert them into positron and electron pairs, we could use that as a diagnostic tool. Now here's a little cartoon, and you're probably sick of seeing this by now, right? You have your neutral particle coming in here. When it hits heavy matter, it creates an electron and a positron, matter and antimatter. So what we've done here is have very heavy material. It's tungsten, and then you put detectors in between the gaps. And so when this happens, you can measure where those particles went. So you measure the trajectories by measuring where the particles went, and then you have things down here which measure the energy. So I've now measured the energy of the proton, or the positron and the electron. And now I want to know where does it point back to, which star in the heavens is there. Well, if you look at this, that's duck soup, right? I mean, it just points. And so you can measure the energy, you can measure the direction, and from that you can find out where things are happening in the night sky. And there is a satellite which was launched a little over a year ago. The major detector here that I just described was built here at SLAC by a dedicated team of particle physicists, and is now orbiting the Earth looking at the mysteries of the cosmos, using matter and antimatter as a tool. Now recall that matter and antimatter, when they annihilate, give off a pair of particles. So here we have a detector. It looks very similar to the artist's conception of what an event looks like at the Atlas detector. If you recall, we had a circular detector that measured trajectories and measured energies. This is very similar to the Fermi space telescope. You measure directions and energies. But it turns out this is not a high-energy physics detector. This is actually a PET scan. Turns out PET stands for positron emission tomography. You actually have radioactive tracers which decay. You inject them into a patient. They then migrate to areas of high metabolism, such as a tumor, which is growing very rapidly, or you can use it for functional imaging in the brain. Wherever you're thinking, you're using up lots of energy, and so these radioactive tracers go there. They emit a positron. It immediately finds itself in the near neighborhood of an electron. They annihilate, and they give off 2 photons, which we as physicists are very good at detecting. So you can then do this millions of times, and when you plot where these tracks intersect, you see here a cross-section of a brain of a normal patient in a PET scan, created from antimatter annihilations within his body. And as I said, you can do this for diagnostic. You can look for tumors, cancerous tumors. You can also look for behavioral differences. This actually is the brain of an Alzheimer's patient, and so you can do diagnostics as well. So I went off on my time just a little while ago. Let me summarize what we learned in this sort of whirlwind tour of high-energy physics, antimatter, et cetera, et cetera. So scramjets exist, at least in prototype form. We're not going to see one landing at SFO anytime soon. I don't think you'd want to, because that sonic boom is really going to wreak havoc on your windows. But definitely, CERN does not have one. I can assure you of that. CERN does exist, as most of you already knew coming in here, but a number of people, including Dr. Langdon, did not know that. It will soon take the lead in high-energy particle physics. It was supposed to start up last fall. It encountered some technical difficulties, as they say, and will be starting up this fall. In the meantime, the Tevatron, running at Fermi National Accelerator Lab, retains the crown of champion high-energy physics laboratory, and they'll probably run for a little bit longer after the LHC turns on, just as a backup. But they will take the lead in high-energy particle collisions. Just a side note, which most of you already knew, every day that you log on and you type HTTP or www, you're using a spin-off of high-energy particle physics. Antimatter is real. I hope I've convinced you of that. It's been around for quite some time. It can be used for nefarious purposes, as in the book, to build a bomb to threaten a city. But I hope I've also convinced you that it can be used for good instead of evil. It's used as a tool of scientific investigation when we create it and allow it to annihilate, to understand exactly what happens with particles and fields. We can use it when we build a space telescope as a diagnostic tool, and we can also use it to save lives and to improve health of patients in PET scans. Now, in 1928, when Dirac predicted the existence of antimatter, and they subsequently discovered it, it revolutionized our understanding of the universe. Theorists, in the meantime, have not been sitting idly by. They have come up with scads of new theories, most of which you may have already heard, string theory, supersymmetry, extra dimensions, all these other theories that predict similar sorts of doublings in the number of particles and the types of interactions that we know to be true in the universe. And so we fully expect that the experiments at the LHC, Atlas I'm rooting for, but CMS I'm sure will be close behind, to revolutionize our understanding, because we have all these predictions and we do have this new collider coming online, which will allow us to study matter, antimatter, and their interactions. So just in closing, we as scientists, as physicists, we appreciate this opportunity. I think we would have had most of you in here, regardless of the fact that this is a blockbuster novel being turned into a major motion picture by Sony Corporation. But we appreciate this opportunity to use that interest to bring you in here and then close the doors and tell you we're not going to tell you about the plot of the book. So we do appreciate that. And we hope that that some of this enthusiasm has rubbed off on you, and that you will follow us as we explore the mysteries of the universe in the next years and the next decades. So in closing, here is the dedication that Dan Brown wrote to Neil Calder, our previous director of communications when he was here. Hope you enjoy the novel. Remember, it's fiction, underline, underline. This is a novel. However, I think I've convinced you that the science behind it, behind much of it, is actually fact. And I think it's fair to say that sometimes fact is indeed stranger than fiction. And with that, I'd like to thank you for your attention.
So the plan from here is we'll take some questions in this setting from Norman, and then we can break up, and there are other various physicists scattered around the room who can also answer some questions after we break up. But first, are there some questions? And they'll be wearing these helmets.
Let me just make one announcement here. For the younger members of the audience who are interested in some outreach here, we have paper cutout and folded models of the Fermi telescope, the satellite, which is in... Let's get to the kids first, but they're down here. Feel free to come on down and pick up a copy of it. Oh, yeah, right. And it used to be called GLAST. It's now Fermi, but, you know, matter, antimatter, annihilation, creation, we change things around all the time.
So we have time for a few questions. I see one up here.
Yeah, if in the beginning, 14 billion years ago, as much antimatter was created as matter, what happened to it?
Exactly. It is indeed. It is indeed. And as I said, you know, one thing is that perhaps it wasn't correct, that there was an imbalance, okay? But take that off the table. It could be that matter behaves differently from antimatter in even the smallest bit. Remember, 14 billion years is a long time for a little bit of difference to accumulate. Or maybe it's out there and it's just not annihilating with matter.
Any other questions for Norman? Here's one.
Is there anybody throwing anything around as far as the idea of dark matter and where that fits in with all of this stuff?
Dark matter. Yes, I should have put that on the list. That's one of these, you know, what the heck is going on out there? And as a matter of fact, looking into the cosmos, looking at astroparticle physics combined with particle physics, it turns out that all the matter that I've just told you about, all this great theory that explains everything, is probably only 5% of what's out there. So, you know, A, it ruins the joke about, oh, everything in response to what's the matter. And B, it gives us this great opportunity to really understand what's going on out there. And we believe that the energy of the Large Hadron Collider will allow us to actually study whether you can create dark matter in the lab.
There's a question way up at the back.
Can you help us understand, in terms of the Higgs boson, how can that give matter?
The Higgs boson. I was very careful not to touch on that. But it is the sort of the last bit of information that's missing from what we call the standard model. So we've been doing this for 50 years now, and we understand a lot about particles. We all understand a lot about how they interact, but we don't really understand how the basic particles, like why is you know, an electron, why does it weigh X? Or why does a quark weigh X? Or why does the top quark weigh so much? We don't really understand that. But we do have some theories about that. And one of the predictions of that theory is that we should be able to discover at the energies of the Large Hadron Collider, or maybe the Tevatron, you know, they're not giving up the hunt yet. They might actually discover a particle called the Higgs boson, which would tie all of this together.
Another question from over here. Yep.
Oh, we're not working on that. No. That was just to show how difficult it would be. We believe that we can understand all we need to know about, you know, basic antimatter by looking at just a few of the elements. We don't see any need to create more than that.
And one more here.
Could you give some examples? You said that creating antimatter on a large basis almost it's very difficult, not very efficient. What are you doing? Like with the experiments?
Oh, experiments. Well, what? Yeah, the question was, it's difficult to make antimatter. What do we do with it when we finally make it? Well, no.
Other than that,
Yes.
kind of experiments are going on, it's not very efficient. They just use that for something.
Right. That's about it. That's about it. Yeah. Yeah. So don't go buy any futures in anti-business X.
Why don't we take this opportunity to thank Norman again, and then we can break up and ask him more questions in private. Thanks a lot, Norman, for a great talk.